We saw that the sieve of Eratosthenes works by crossing out multiples of primes. But then if the number that we are looking at is very large, then it takes a lot of memory because, we got to make a sieve that large. So for example, if we are looking to, let's say, find all primes till 10,000, we have to create a sieve that has 10,000 items and then cross out all the multiples of the primes until square root of 10,000. It turns out that the segmented sieve handles this differently. It works by breaking the problem down into several pieces and then handling them one by one. The key idea is that, look, like I said, to get a list of prime numbers till say 10,000, all we need to do is to have a list of all primes till 100 and then mark out all the multiples. So what we can do is to run the sieve once until 100. Now this gives us the base list of primes. Subsequently, for all other segments, so we basically make segments of 100, for example, we get the list of primes. This base list of primes can be used to mark out composite numbers in every subsequent segment. Again, visualization is going to make it clear. So let's do that. So here we have, for example, a sieve until 100 like usual. So I got the multiples of 2. Now I'm getting the multiples of 3. I get multiples of 5, multiples of 7, multiples of 11. Actually, that 7 was sufficient. And we realize that the base primes are 2 until, let's say, 2, 3, 5, 7, 11 until 97. So these are the base primes which have been found until square root of 10,000, which is 100. So now I load my next segment, which is from 101 to 200. All I need to do is to mark out the multiples of this list of base primes. So I do that, all multiples of 2, for example, being marked out over here. I go to multiples of 3, multiples of 5, multiples of 7, multiples of 11, multiples of 13. In fact, we are done because the next prime here, remember, is 17, and 17 square is more than 200. So I'm done for this segment. I move to the next segment, which is 201 to 300. Now, once again, I go and mark out multiples of 2, multiples of, say 3, multiples of 5, multiples of 7. In this case, I will go until multiples of, say, 17. So there's 13 times 23. The next one is 17. So I got marked multiples of 17. That's why I can. So that's how the sieve works. This is interesting because each of these segments can potentially be handled in parallel because we have the list of primes available and we can then handle these sieves parallelly, which can be very, very efficient in a, let's say, in a parallel computing setup. So now with this idea in, now, having seen how this works, we can get an idea for how to write the code. In fact, like I said, we decide the segment size. Typically, we want the segment size to be, let's say square root of, till this number. That makes it simpler. Basically, I determine how many segments are there. So in this case, I'm just making it 10 just for the sake of testing. I get the list of base primes by running the sieve once until 100. Now, this base primes is, remember, a list. Now I'm interested in new primes, which will be updated every segment. So I just go and load a new segment. Again, this comprehension here. Basically I just get the next segment, like I was getting 101 to 200, 201 to 300, and so on and so forth. And I just run this over base primes. However, remember, I still need to run this only till my square of the primes, being considered is less than equal to the last number in the present segment. Now, the next part here is interesting. How do I start this? Where I start this, let's say the first number in the segment. We'll talk about this in a moment, but basically the idea is very, very similar to earlier. Wherever I find that there's a multiple of these primes, I go and mark this to false, and that gives me the segment primes for this particular segment. Like I said, the interesting bit is how do I start the starting point of a next segment? Well, remember in the case of, let's say, the basic sieve, we always started from 2 because 2 was the first prime number. But here we have to start with a multiple of 2, which is the first multiple of 2 falling in, let's say, the range of the segment. In fact, in general, we have to start with any multiple of any prime number, which is the first multiple that falls in the range. And the way we can find this is, look, we can look at the very first number. Number 0, remember, numbers is a segment basically. So number 0 is the first number. I can find out how much is the gap between the number and the modulo. Again, the example will make it clear, and I do one more modulo. So we will see what this means. Basically, let's say, number 0 is 101 and p is 7. So basically the first multiple of 7, that is, let's say after 101 is actually 105, and we can find this out because it's, well, look, if I were to do 100 modulo 7, basically, sorry, 101 modulo 7, I'm going to get 3, and hence I must add 4 to this, right? So that's what is going on here. Now you might wonder, why do I need a second modulo? Well, the reason I need this is, in fact, is clear from this example. So if I take 201 and p is 3, well, the first number itself is the multiple. If I were to, however, do 3 minus 201 modulo 3, I'll end up to 204. I'll end up missing 201. So you remember, these small points are very, very important. So I will do a second modulo. This is really cool. So this will take care of the case where the first number, number 0 itself, is a multiple. And that's why I started 201. So this is sort of the main idea of the code. Think about it. Very, very interesting. Happy to discuss as always. So here's my code for the for the segmented sieve. Essentially, like I said, first I get the base primes, and then I run this over all the segments, load a new list of numbers, and when I run this code, for exact example that I've shown, I'm printing the different segment, the primes that I'm getting. So for example, between 101 to 200, I've got this list of primes, and 200 to 300, I've got this list of primes, and so on and so forth. You notice how this list is being formed with just a requirement of memory of 100. And as I said, in a parallel computing setup, in fact, this different segments could be handed over to different CPUs to create this entire list really, really efficiently. And that is why segmented sieve is a more attractive idea compared to blindly running the sieve over the entire, let's say, 10,000 points. I would say a very nice example of how we are able to split the problem into pieces and handle these pieces individually. Very, very interesting. This video is a part of the WiByte Algorithms and Olympiad track. Do look at our website www.wibyte.in and forever enjoy coding. Take care. Thank you so much. Bye bye.